Okay,
Yeah.
so today Selman is going to talk about categorical approach to the Deutsch-Jozsa algorithm, and yes, so we will see some applications. Please go ahead.
Okay, sure thing. So in the previous couple of weeks, we talked about monoids, comonoids, and their relation to no deleting slash copying, and I should probably add no uniform. At least in the categorical language, we add this piece, but it corresponds to no deleting and no copying that we know from quantum mechanics. Last week, Victor talked about Frobenius structures. So if along the way we maybe don't remember some of the properties, we can sort of go over them. I'll just take them as a given for the time being, maybe a good assumption, maybe not. And in addition to Frobenius structures, we then were able to introduce in a categorical way I'll call this complementarity, but I'm not sure that they use this term specifically. They talk about complementary Frobenius structures. They talk about complementary bases. I don't know if they use this word specifically. So this week we're going to want to sort of leverage these sort of structures and the basic sort of properties that we built up to talk about Deutsch-Jozsa problem. So because I lack any real creativity, the way that I structure these these talks is I'm going to give the quantum mechanical treatment from the outset because that's what I'm comfortable with, and then I will try to highlight the pieces that go into the categorical treatment and probably just hand wave some stuff by saying, oh, but it works quantum mechanics. Okay. Yeah. So in the other talks, the opposite thing happens where, people rely more heavily on the thing that they're comfortable with. So you get this preliminary about Frobenius and you get this stuff about monoids, and it's like, so I'm the complement of that, I guess. Yeah. So the Deutsch-Jozsa problem is as follows. It's one of these instances of a fairly simple problem to state. It doesn't turn out to be entirely useful. So this is a problem that can be solved in a more efficient manner relative to your definition of complexity on a quantum computer than you would on a strictly classical computer. It's not strictly a very useful problem stated exactly like this, but it just sort of gives a highlight for what kinds of things you can do with a quantum computer or a quantum device that you can't classically. So the idea is as follows. You have some function 0, 1, n. I will maybe sometimes write this like b to the n or something if I'm feeling particularly lazy. So we have a function like so, and we're promised that it's one of two things, such that f is either it's constant, which I will explain, but I mean, it's kind of straightforward. It's exactly what you would expect, or balanced. We're promised that it's one of these two things. Of course, the functions f, there are many different functions, and they might not fit this particular categorization, but we're just strictly restricting ourselves to these two cases. Constant, so as trivial as it might seem, let's just go ahead and say that it's some f of x sorry, equals S of, and maybe I will also call this B, where, sorry, this is some 0 or 1 for every x in b to the n. There's also a sort of nice picture that goes along with this. Yeah, sure. Did I do something?
People know what you mean by constant.
Yeah. Okay.
There is S and B such that
For all x. So for every x, there is it's
reads
some
like,
value.
yeah.
Does it read the wrong way? Yeah.
yeah, that reads fx is some S in B for all x, which is
Math is my second language. I don't know. So okay, yeah. So it could be sort of semantically back, like a little awkward. Sorry. Yeah. For some permutation of these.
But I think if you do the same thing, but read it.
Okay, yeah. So the idea here, and maybe I will put it here just to give myself some more space, is that you have some function f like this that is going to factor through, when we're talking about sets, for example, the singleton. Like this.
Now I'm proud.
Yeah.
This is categorical.
Yeah. Yeah, I mean, who would have thought you should take this very basic idea and make it into a diagram? But so balanced is a little bit more awkward to state. And for balanced, I'm just sort of going to give the idea for what this means. It just means you have half of the images, so you always have some even number of images. Half of the images are going to go to 0, half of them are going to go to 1. That's it. I'm going to write it down, but it's more awkward to write it down than it is to just say it. You just have some function, and
you can just say f inverse of 0. There's a bijection between f inverse of 0 and f inverse of 2.
okay.
Subsets have equal number of values.
Okay,
That's
so
all you want to say.
maybe I can say something like this: the set of f inverse 0 equals f inverse 1. Is that? I think.
You don't need the set traces, but yes.
Yes.
Yeah. Okay.
F inverse of 0 is a set.
Ah,
You
yes.
don't need
Okay. Yeah. For sure. Yes, I don't need
just
these.
keep the absolute values.
Very nice. Okay. So yeah, that's much cleaner to state like this. So then, what is the Deutsch-Jozsa problem? And it's as follows: determine with as few queries to a computing device as possible whether f is constant or balanced. Okay. So the classical solution to this is as basic as you might hope. Basically, the idea is as follows. Again, I'll just explain it. You can imagine that I have the images, so I will just sort of pictorially take this. I have a set of images for each element in b to the n, and the images could be something like 0, 0, such that there's exactly 1/2 of all of them here, and then 1, 1. This is kind of the worst case for our problem. So let me explain. Classically, what you're going to do is you're just going to sort of query this device. I'm going to take one possible element of b to the n, and you're going to check its image. That's what the computing device is going to tell you. Now, it could be that for the first n queries that you do, you get 0 every single time. And then what you really need is half of the number of elements plus 1 in the worst case to see whether this thing is constant or balanced. Because if it's 0, 0, 0, 0 up to some point, you don't really know whether it's constant or balanced. Now, if it was the case that you got a 0 and a 1, in principle, you could also solve the problem if you were lucky in, 2 steps or something. Over 2. Oh, 2. Yeah, got you. Yeah. Yes, in the worst case. Now, with the quantum solution, so let's just say this. So in the worst case, requires something like 2 to the n minus 1 plus 1 queries. A classical device. Okay, so let's talk about the quantum sort of approach to this. So in the quantum approach, what we really have we have qubits, we have Hilbert spaces, and we have unitaries and measurements and stuff like this. So the notion of a function like this has to be embedded into that sort of tuple of structures. So what we instead do, so for the quantum solution, let's consider some Hilbert space where I'm going to deliberately write this in a not economical way. The basic idea is that we'll have some sort of system A, which is going to be composed of n qubits, and some system B, which is just a single qubit. And we're also going to have, instead of having this function directly act on something like our basis or something, we're actually going to have something a little bit different. We're going to have f. I will draw some squiggly to just indicate that there's some relationship. Unless somebody is going to tell me, well, that's not a real map or something. So I don't know, just relationship to unitaries acting on that Hilbert space, such that if I have UF acting on, so this is a bit string. So this will be some sequence of n zeros and ones. Tensor Y. This is a single bit, a 0 or 1. And maybe to indicate that this is some long bit string, I guess I changed notations. The vector, I mean, this could also be a vector, just to make it clear what's going on. That this unitary is defined by this relationship, x, y, modulo 2 sum with f of x. Now, the circuit that we're going to draw will be as follows. So we have our initial input state will be chosen to be zeros. And we have this ancillary or auxiliary qubit will be in the state 1. We apply a tensor product of Hadamards, and I will remind you guys how these act. And a single Hadamard here. I guess I could have just combined it into one, but let's just keep the two things distinct. And this is UF. We again act by Hadamards, and then we measure in the computational basis here. I will just call it X. And of course, there's an output state, but it will turn out to not be particularly important, actually, and that's a sort of important point to emphasize. It will be useful to organize things in the following way. I might as well distinguish this. So these are my different times, T0, T1, after I apply this one, T2, and T3. Probably will suffice. And to, I'm sure, Reddy's delight, I'm going to actually work through the algebra here just in painstaking fashion. So just recall, we have that this operator H does the following, such that its action on, if I take H on any computational basis state, X, which could be 0 or 1, then this is going to be equal to 1 over 0 plus negative 1 to the X, something like this. Also, just to make connections to something that Victor talked about last week, or 2 weeks ago rather, there's this sort of interesting property. The dimension of this Hilbert space is 2. So if I take the inner product, the bra and the ket, and I might call this plus or minus, depending on the initial input X. Not a great notation, but I will put just X here. So if I put X and then plus or minus here, you see that I will get, regardless of whether X is 0 or 1, I'm going to get that this is 1 over square root of 2. So I don't remember if Victor explicitly wrote this, said this last or 2 weeks ago, but there's this notion of complementary Frobenius structures, and then also complementary, there's a bijective correspondence to complementary bases. And so these are an example of complementary bases. When you take the inner product for all choices of X or plus or minus, you get 1 over the square root of the dimension. I could be off by a factor there. Maybe they define it as it has to be equal to 1, in which case multiply by this factor. But it's the same factor. I could be off on that. Yeah, so that's what I wanted to say. These are complementary bases. Any questions so far? We're good? So now we have, what does this evolution look like? So in the initial state, we have, and I will not belabor these points too much because it is ultimately just algebra, but it's probably worth going through it at least once. Sorry. Okay. So we have this. So what's going to happen when I apply this Hadamard here? What happens when I apply it here is I get a minus state. We know exactly how it acts. When I have a tensor product of these, I'm going to be mapping each of these zeros to plus states. And because there are n of these, and I'm applying h on every single one of them, I'm going to be getting the state 0 plus up to some overall 1 over square root of 2. Essentially, what I'm going to get is an even superposition of every single possible bit string. Does that seem plausible? You guys see that? Okay. So this is 0 after the first step, and we apply you will have 1 over 2 to the n plus 1 sum over all bit strings x tensor. I have this here. Okay, let's keep going. We know exactly how this thing acts. I gave the rule for that over here. So it's not going to be hard to see that it works out like this. So 1 over 2. Oh, sorry, over 2. Is that what you meant? 2 to the n plus 1 over 2. I have 1 square root of 2 for each n plus 1 factor. And the whole thing, yeah, it looks kind of weird if I write the over 2 on the whole thing. But I can, yeah, sorry. So this is going to result from an application of UF on here. Instead of actually just writing that out, let's just work out what it should be. And it will be just in the most naive possible way. I might stop writing that at some point. Tensor, this will be f of x, because we're just adding 0, minus f of x. This is modulo 2, 1 like this. Now, let's just sort of distinguish a couple of cases real quick. So if f of x is equal to 0, then we get back the same state. And if it's equal to 1, then we have precisely the states flipped. So I have 1 over 2 to the n plus 1 over 2, sum negative 1 f of x tensor 0. And probably I can just start writing this as minus from now on, because nothing else will happen to this right-hand side. Finally, we end up, so by the way, it should be noted, I don't know if I'll have time to emphasize it later. So in Vicary Heunen, they kind of, and you can always do this, they consider this the state preparation. Basically, they assume that you start with this even superposition, this even superposition right here from the outset. And then they talk about measuring in not this z tensor to the n basis rather, but they talk about this whole thing as being a measurement of in the x tensor n basis. Just a slight shift in perspective. It's not going to end up being too important, I don't think. What did we want to do here? Okay. Okay, yeah, let's try and fit it in here. So finally, we're going to apply this one right here. And I will have to do a little bit of explaining for this. Sum x some z negative 1 to the f of x plus x dot z. This is just normal Euclidean inner product. Z tensor. Let's get rid of this 1 here. And over 2. There's another factor of square root of 2's coming now. Okay, I will explain that in a moment then. This is 1 over 2 to the n. And this one will just be minus instead of writing that whole thing. Where does this come from? So let me just explain briefly. It's probably easiest to just do a couple of examples. What's happening here is I'm applying this Hadamard gate to each of these bit strings here. Well, what's going to end up happening is you're going to pick up a minus sign depending precisely on. So each of these bit strings here are some zeros and ones. They're going to be changed using this relationship to pluses and minuses. So you have this double sum. And you're going to end up picking up a minus sign depending precisely on the bit string x here. So let's just look at an example. So if I do Hadamard to the 2 on my state 0, 1, what am I going to get? I'm going to get precisely plus, minus. And when you expand that out, that's going to be something like 1/2, 0, 0, plus minus 0, 1, plus 1, 0, minus 1, 1. So you end up picking up these minus signs. You can show it's not hard that it's going to look precisely like this. So. Okay, so the final thing, what have we done here? So how do we solve the Deutsch-Jozsa problem now is we're going to have a witness for whether our function is constant or balanced. Namely, we're going to perform a measurement in this basis, and we're going to look at the outcome 0. What's the probability of the all 0 bit string? So if I want to find the probability for the all 0 bit string, by the way, I always know that this is going to be a minus, so I can always just also perform a measurement here in the plus basis, or x basis rather. So I will just look at the following. Imagine we do 1 tensored with 0 on psi 3. Now what's that going to look like? It's going to pick out precisely this z that's equal to 0 because they're otherwise orthonormal. So I collapse this and I get just sum over sum x negative 1 to the f of x. And I forgot a very important piece, which is this constant 1 over 2 to the n. Negative 1 f of x. Yes. Okay, so this is the amplitude that I'm working with. Can anyone see what this answer is? So we should distinguish two cases. Sorry, yeah. So this is one step. So now if we look at we should look at constant first. It's easiest to see. Okay, so if this function's constant, then we get exactly. So and let's just call this, okay, I will just say 1 tensored 0 on this is equal to plus or minus 1, which means that the probability of getting, and I will just focus on the 0 part, the probability of getting 0 given that the function f is equal to constant and you have some state psi3 is equal to the square root of plus or this modulus squared. So it's just equal to 1. So we always have, so if the function is constant, then we know for a fact that we will always get this output with unit probability 0. Now, the reason that we can actually distinguish the two cases in a single query is because, and I can get rid of this. In the balance case, any guesses for what the probability of getting 0, the all 0-bit string in the balance cases? But it's, so if it's constant, then you get that this probability is equal to 1. So I kind of understood what you're saying to be like 1 minus that. So yeah. 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 So yeah, 0. Yeah. 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 Yeah, exactly. You just look at this same expression and you get that this whole thing equals 0 when it's balanced. So instead of writing down this whole amplitude, I will just write this, given f equals. And I suppose in principle, I should distinguish that this is balanced rather than this is a different psi3 constant. And it equals 0 squared equals 0. Okay, so yeah, that was a lot of algebra. So let's see if we can do better with just drawing pictures, more or less. Okay, so oops. For the categorical treatment, remind me, I didn't have notes on this, but did we talk about phase and phase shift last week, Victor, or? Okay, yeah, I also didn't have it in my notes, but I was just making sure. So, and now you will probably, if you don't remember, have to sort of ask me or prod me to give you some definitions if some of the terms that I introduced here are unclear. So we have in a monoidal dagger category, with and a Frobenius structure A and a state. Maybe I wrote this a little bit awkward English-wise, but I to A is a phase if it satisfies the following. Equals this, and if you remember, this thing was actually written down, I believe at some point by Victor. We didn't make the connection to, okay. These are basis elements in A. Something like this. So actually, there's a nice analog of this in, okay, so I should probably, monoidal category, I think we're okay with. The dagger, okay, monoidal dagger category, that part is also okay. I think that this part is straightforward, I guess, to some extent. And we also have, maybe I should give an example first. Let's see if I have it here. So if we look at fhelb, then, sorry, yeah?
This formula is weird because the symbol that you're using, you mean sum over AI in A?
Yes. Okay, that is awkward. Okay, just this should be a different indexing set. Like there's no relationship between this A and those A's.
Oh, okay.
Yeah, sorry, that's a completely good point. Let's do this. B. In principle, B is a basis for A, and B's are, and this should be a B as well. These are copyable states. And a phase, I mean, the intuition here is, and that's what the example is for, is that if I have my basis states being my computational basis, something like this, then what are the phases? The phases are going to be states that are equal superpositions over my basis states, more or less equal superpositions over my basis states. And so something like a phase would be, for example, maybe I just write it here. So 0 plus 1 would be 1 when I'm talking about C2. And in general, if I'm talking about something like Cn, and I have a basis I equals 1 to n, then a phase will be some state that's of the form EI equals 1 to n, where psi i's are complex numbers and their modulus is equal to 1. So the phase shift, so if we have some map like this, this morphism is a phase shift if it satisfies, or it's defined more or less like this. You have, using the same definitions as over here, or maybe I should do it like phase shift is defined as this sort of thing.
For A of A.
For
For A of A.
Yeah, exactly, yes, for AFAs. So I got rid of precisely the thing that I needed, but the idea is that when we applied this Hadamard onto our bit strings, we were obtaining phase shifted vectors. That's what the Hadamard does for, you know, tensor products of qubits. So let's see. Okay, so this part is going to tell us that, no, okay, I will skip this for now, actually. Question?
He's asking on the left-hand side.
Yes. Did you think this was an A, maybe?
No, the one in the circle.
Oh, yeah, my handwriting just terrible. Not sure that's better.
Now it really looks like an A. Shouldn't that be
That
full?
should be a P and the other one.
Let me check.
Yeah, you're defining
Yes,
the morphism.
yes, that's what it should be because this is a morphism. So yes, this was supposed to be an A, but this one was not a phi, but an A. But it's a kind of weird abuse of terminology here. So let's call this phi again and call this phi. I think that's better. Yes. Okay. So we're good here. And okay. Yeah, we have to define some other stuff as well. So if we want to talk about this Deutsch-Jozsa, we need to introduce the notion of an oracle. So in a monoidal dagger category, I will be lazy. Given dagger Frobenius structures A and B, I guess this is the same thing with white. An oracle is a morphism B that makes the following morphism unitary. So if we have something like this, by their dots you shall know them. That's how I do it. Okay. F circle. So this is A, B, B, A. So we want this thing to be, we want this F to be such that this whole thing is the composite unitary on A tensor B is unitary. Maybe an example would be good here. What's the time? Okay, good. So the example is going to be something like this. Hopefully I'll be able to highlight the main point. But if you have in some finite set, for some finite set, you have S and T finite, and you have some morphism F between them, then we can this sort of induces a morphism between Hilbert spaces. How does that work? So if in this previous example we had A equal to the Hilbert space H, what do I mean by this? I mean precisely the Hilbert space of the proper dimensionality and everything such that we map the elements of this finite set two basis elements in HS. And let's let B equal to HT in the same sense. Then we have that there's some, I guess, induced map. I don't think we should use the same A to B such that we have that the vector A gets mapped to F of A in terms of vectors in these bases. Quizzical puzzled look. I don't know, Walker seems...
He probably wants to say that it's pretty...
Yeah, that's what they said in the book, but I...
That's exactly what
Yeah, no, that's precisely what they said in the book, but I...
So the example that you're giving though is an oracle in finite Hilbert space.
Yes.
What I was confused by was just writing F set because
Okay, sorry. Yeah, just to make it clear that S and T are finite sets, and then we can just deal with finite Hilbert spaces in the usual way. Yeah, I think Reddy said it, but for me, that's not a language that, if I said something about freely generated Hilbert space, I would be almost surely wrong about it, but it intuitively makes sense. Okay, so if we have that EI is a basis for B that is mutually unbiased, with respect to the basis F of A, and we have that the norm of each EI is, I guess norm squared, I should say, is equal to the dimension of B. Then we have a sort of structure here. How does this work? We have this map that we can define here. EI F. Yes. So it's mutually unbiased if I take the inner product between this vector and this one, and for all elements of each, you get 1 over the square root of the dimension. The idea is supposed to be that when you compute the probability, something like this, EI F of AJ equals 1 over the dimension of B. This should be something like a uniform probability distribution. Yeah, so an example of this would be these X and Z bases satisfy this property. Physically, this is, by the way, kind of exactly the reason that you talk about complementarity. The example that most people might know if they take undergraduate quantum mechanics is position and momentum. But because of the infinite dimensional nature of that, it's kind of awkward to write it down in like a minute or two. Because to say that something is mutually unbiased, you have to have a uniform probability distribution, but your space is infinite. And so now it's kind of a little bit wacky to talk about it. So that's probably the most prominent example where this complementary notion comes from, but it's probably a little bit awkward mathematically to write it down. And I'm certainly not going to try. Lest Walker just be like, well, well, is that inside the topology, or did you, what did you?
No, I mean the issue here is the operators.
Yeah, exactly. The operators are unbounded, and so then if you want to talk about the eigenspace of the, yeah, and that's what I mean by, you have to, rigged Hilbert spaces or something. Okay, so we have this, and I didn't finish the statement. So we have that this is mapped to something that's something like a scalar times the original vector that we have. Now, it will be obvious to see that this is unitary if we have that this thing is modulus 1. In fact, it's not hard to show that, but I will just sidestep it for now. It can be shown that is precisely equal to 1 for all choices of EI and FA, so that this is precisely unitary. Okay, so now we can talk about this Deutsch-Jozsa. Okay, so let's go with this. I think this should be filled in. So this idea, okay, so this is equivalent to the circuit that I drew, plus some caveats. So I mentioned this before, just we're talking about this initial state preparation here is of a specific form. So this is going to be like a even superposition. This part is essentially equal to the part that I wrote where, so it'll be something like, this is the part where you get h to the n acting on, they sort of just sidestep that. Similarly, this piece, they talk about measuring in the n-fold tensor x basis. So this one is going to be something like h tensor n and measurement in the z basis. This part here, and I will explain this stuff actually just. Okay, so what do we have here? Here, this is going to be some initial state preparation where this is a so-called copyable state. We kind of understand what we mean by that when we generalize it, because when we started with the quantum circuit, this was a 1. Hold on. No, but that's a little bit contradictory. Sorry, what I'm going through now is that this is a copyable state, but they didn't apply a Hadamard. It could be copyable with respect to a different Frobenius structure. Let me check real quick. Sorry, just want to remember what they write for. To are the x basis, write B for, okay, so they're taking this to be the analog of the minus state, which makes sense. So they've already applied the Hadamard. Okay. Sorry. Yeah, this is what I was not sure about. This one is. So what's going on here? We actually have two Frobenius structures. So that's what makes, I think Victor mentioned this last time, when you have sort of complementary Frobenius structures, there's two of them and they satisfy some Frobenius laws. And so this is black dots for one of them, white dots for the others. Okay, so this is a copyable state with respect to this one. Okay, that makes more sense. So, and there are some scalar factors that I'm not.
And F here is an oracle.
Yes, and F here is an oracle. And let us assume that this state is coming from some finite set with n elements, but we could just take that for concreteness to be 1 over 2 to the n over 2. That's scalar factor. And then also the same thing over here is going to, just because of the way that we define these states, you have to introduce this additional factor. 2 to the n over 2. Okay, now we can. So the major simplification here, and maybe I will just write it down, and then we'll introduce the lemma that makes it happen. But using the lemma that I'm going to introduce in a second, what ends up happening is that this thing can be written as B F B, and there's an additional factor of 2 over 2 to the n. Okay, so let's see where this is coming from. So for a mutative dagger, I'll write it. Dagger. Frobenius structure. The following holds. For every copyable state. And it's the following. We have something like this. Equals So you can sort of see how this comes into play. We have something that looks just like that right here. So when you insert this identity, we have that the axioms are more or less satisfied. We have that this is a copyable state. And so we just insert instead this projection looking operation. Don't need that. Do I need to do that? Well, okay, we can just see it from here. So if I replace, this will have B's here. What I will instead have here is that I have this wire going up to F, and it will be capped off with a B. But you also have this piece here. So, yes. No, there's some additional factors that I have to work out. So let's let's actually work it out a little bit more explicitly. So, because it's important that we get the actual factors correct. Okay, I will divert the proof until later if we have time. So in fact, if we just look at this piece here, what is the actual thing that we get? So let me work it out over here. B F and close dot. So this is just one piece of that without the scalar part. So let's see how the scalar part comes around. So the scalar part is coming from the following, that we have that what? Okay, sorry. Yes, here we go. This is where the scalar part comes in. So let's actually consider the two cases f. So f is an oracle. Let's consider f being related to some constant function versus some balanced function. So that's the piece that I'm... Okay, so, and let's actually just disregard this additional piece for a moment. So if we just look at this and we say that we know that f is equal to a constant function, then we actually had the definition of a constant function that we had before, which was this piece, if you remember, is going to look something like a state preparation for some x. You initiate some state, and it's going to go to b. Remember, this thing is going to factor through some singleton stat, or more or less, you map f to the unit, and then from the unit to x. So you actually get that this thing will be x and this piece just like this. Now, this piece right here is, we have to be careful with the normalizations, but this one is, remember, I had to introduce a 1 over square root of 2. Man, my factors are all messed up. Where did I include that here? 1 over square root n squared, 1 over square root n squared. So this one does not have any problems with the square roots. If I look at this inner product, then I should get a square root of 2. Where's that coming from? This one is easier to see. So when we look at this one, yes, that's right. Yeah, but I should be getting a square root of 2 on the numerator. Yeah, so I have to see where I dropped the square root of 2. But so this one is, I have 2 of these even superpositions, and I'm taking their inner product. So actually, this one will be n to the 1/2 squared. And then, yes, because remember, I had to introduce the normalizations here. So without the normalizations that I look at here, I will have a factor of n to the 1. Sorry, that's a different notation I was using, like this. And then this one is supposed to be square root of 2. And you'll have to forgive me, I have to look to see if I messed up something with the normalization over here. But this one's supposed to get square root of 2. And what you see is that I will have the 2 over the n. No, it's okay. I'm supposed to get 1 over square root of 2 here. That's exactly what I want. Okay. And so then I have to explain why I got the factor of square root of 2 on the top over here. Okay, I will come back to that in a second. But at least this is exactly what I expected it to be. So I get a factor of 2 to the n, 1 over square root of 2. And eventually I will, when I put that in here, you'll get exactly 1 here. Now in the case that this is balanced, when it's balanced, it's kind of straightforward to see, but hopefully if I have something like this, and this is my input, this is my output wire, then I will have that because this state right here is a sum over some computational basis, you more or less have that this is I mean, this calculation more or less mimics the exact same one in the quantum mechanical case. I guess that's not surprising. Yeah, so there's no problems with the factors here. I have to go back to the square root of 2 at some point. Okay, any questions? Yeah, that was a little bit cluttered the way that I explained that, but the main idea is just that we can use this lemma and basically break this down, and what you get is that what this lemma buys us is precisely why we end up not caring about the last qubit anyway. It doesn't show up into the calculations at all, and sort of this is a nice categorical sort of way of seeing why we don't actually care about, we don't measure it, we don't do anything with it after the unitary. So that's kind of interesting to see that. And more or less, this is exactly sort of just everything is concentrated on the first n qubits, exactly as you might hope, and then with the output being on a single qubit. Actually, that is more or less, if there's no questions, that's more or less what I had planned to say.
Could you say something about number of queries? Like addressing
Oh.
the original problem?
Oh, I thought that I did in the original demonstration of the quantum part, so it was a little bit lost in my mangled explanation here. But the idea is that because when I measure in the z basis, I get the I get that 0-bit string in my device. When I measure that system, I get the 0-bit string with 100% probability if it's constant, right? So what that means is that I do a measurement in that basis, I get this 0-bit string, and what I can also show is that I never get that bit string if the function is, the probability is 0 if the function is balanced. Which means that if I just run this thing once and I get the answer 0 vector or not, then it only requires a single query, right? Because in the constant case, it's always going to be 0. And so as soon as I see that once, I know. I don't even have to do it a second time.
Okay, this I must confess confused me as well, but I think for a slightly different reason. Because in your initial like 2 to the n minus 1 plus 1 queries case,
Yeah.
you're treating looking at each element of a bit string as a separate query. But here you're saying you have a bit string and deciding whether it is the 0-bit string or not the 0-bit string is only one query. Which
in one case you have a quantum oracle, the other one
Yeah.
classical.
sure, but in both cases at the end you have a bit like in the classical case you could say you apply the function to everything, you have a bit string. In both cases you have a bit string. Why at the end of this whole process? Why is one only one query and one not?
You're counting basically the number of times you query. Right?
Yeah, it's the number of times you have to run the circuit. So I could draw an analogous classical circuit.
Okay.
Although they're
Yeah, that's
Okay,
a good point that you make. Yeah, they're not really comparable. The notion of oracles are different.
Okay.
Yeah, in the first one, the oracle is just the thing that spits out the numbers for you. Here, an oracle is the thing that gives you a specific unitary, which
Okay. So what does it mean to say this is more efficient then?
well, because at the end of the day, the number of times you have to actually feed it into a particular computing device is certifiably less.
Okay.
Okay, any other questions? Any questions on Zoom? Okay, so now let's thank Salman.
Thank you.